Assalamu alaikum and good afternoon, everyone. First of all, I would like to express my sincere gratitude to our respectful teacher, Ristisha, for giving us the opportunity to present today. Before I begin, let me introduce my team members. I'm Nahidul Islam Pranto, and with me, I have group mates MD Al-amin, Sayham Kayas, MD Yeasir Arafat Toufick. Together, we'll be presenting our topic, which is process in operating system. Next slide. First, we have to know what is an operating system. To understand process, we first need to know operating system is. An operating system or OS is type of system software that manages all computer, hardware and software resources. It works a bridge between user and hardware. Some of its main include process management, memory management, file management system, and input-output device management system. Common example of operating system are Windows, Macros, Linux, and etc. Next slide. Definition of process. A process is simply a program in executions. When a program is loaded into memory and starts running, it becomes process. It is an active entity that uses CPU time, memory, files, input-output devices. The operating system is responsible creating process, scheduling time, managing time, and finally terminating them when they are done. Next slide. Process components. There are several components in a process. First of all, text section, data sections, text sections, and heap sections. And last one is process control block, which is so much important in process components. This is a special data structure maintained by the operating system. It stores important information like process, program counter, CPU register, priority, and scheduling information, memory management details, and so many other things. Next slide. Process states overview. A process moves through different states from start to end. First of all, new, the process is being created. Then ready, the process is prepared and waited for the CPU. Running, the CPU is currently executing an instructions. Waiting and blocked, the process is waiting for an event such as import output completion. And terminated, the process has finished executions or has been stopped. Now I would like to invite MD Al-amin to continue this presentation and others. Thank you.
Thank you, Pranto. Assalamu alaikum, ma'am. This is Al-amin. My ID last four digit is 1935. So today I will cover process control block. Here we have four subtopic: process state diagram, state model. Second is state transition. Third, process control block (PCBB), and fourth is context switch. So next slide. So now I am talking about process state diagram. So we know about that process state we have in operating system is 5 state. So process does not stay to in one state. It moves through several states during to its lifetime. And also most common thing we have are 5 state to working in process starting new and to the terminal state. So at first we have new to process. It's then think that there is a starting point and also its process created and or admitted into the system. And second is ready. The process is loaded in the memory and waiting for the CPU. And also it's not running yet, but it's ready to the running. And third is running. The process is currently using the CPU. Only one process can be in the running state per once. And fourth is waiting or blocked. If the process needs I/O, such as reading for the disk or waiting for the user's input, it cannot continue. So it's moved to the block state. And fifth is terminate. It means the operating system finished the process execution. When the process is finished to the execute, to stop in the OS, it's entered the terminate state. And all of the state in the process It's very important to manage this state to ensuring smooth multitasking and also to efficient in the CPU utilization. Next slide. Now I am talking about the state congestion. So here we have six state congestion. So at first new to the ready, ready to the running, and running to the ready, and running to the blocked, and blocked to the ready, and last running to the terminal state. So now talking about it's ready to the new to the ready. So at first OS is creating a new process, and then OS accept the newly created process to and put it to the ready queue for the execution, and then ready and running. The CPU scheduling select the process from to the ready queue and give it to the CPU, and then running on to the ready. So if the time slice finish or the process is permitted by the higher priority jobs, then it's returning to the ready state. Now talking about running to the blocked. So the process performs input output waiting for the resources, and also since it cannot to the continuing, it's the OS blocked ID. So blocked to the ready. When the input and output is complete or resources becoming available, then the process moves to the back to the ready queue and to the ready state. And then it's running to the terminate state. It's finished. When the execution is complete, then it's moved to the terminate state. When the job is complete, then OS move the process in from the system. So all of this state congestion helps to the OS system to according multitasking efficiently. Next slide. Now talking about PCB, process control block. Here we know about that OS is a representation in the operating system by the special data structure. It's called process control block or PCB. It's important to the identify card of the process, and also it's containing all the essential information the operating system needs to manage the process to starting state to the terminate state, new to the terminate. So here we have things is PID, process ID. It's an unique identifier of the process. And second is program counter. It's the holding the next state execution, which next instruction will be executed. And then CPU registers its value to the must be restored after context switch. After the context switch, which value will be restored for the process execution. Scheduling information. It's the priority or process state. So which process will be executed next or now executing? It depends on the priority process state. So now talking about the memory management information, it will be have page table, page, or we have also the linked registration register, and that input output state is that listen or opening list to the open files input output devices to assign users input waiting for the execution of the process output. It's depending on the input output status. Accounting information is it's that CPU time up to runtime use, time limitations, and so on. In the PCB block, where it process are change the state, and also it's the operating system update the PCB. It's keep to track of everything. Next slide. Now I am talking about the context switch. So it means context switch mean that CPU switch from one process to the another process. It's it is safely to the OS must save the current state, process state in the PC block, and then loaded the state of the next process. It means that when we switch one state to the another state for the it's the context switch. When we move to one state to another state, we need to save the previous state and then load to the next state for the execution. So we have the context switch. What's happening? It will be time slice expiring. It had a higher priority process arrives, have process performance, input output, or just blocked. Or if the process will be blocked, we have interrupt occurrence. So we have that. For we have doing context switch. So here talking about the time slice expire. So when the process is running, it's used to allocate the CPU runtimes, and also so that the CPU stops it and give us the CPU to the another process. And the high priority process arrives mean that when a new process is arrive with the high priority and it will also become ready, then focusing on to the CPU to switch from the current state process execution to the high priority important upcoming process. Process performance to input output and get blocked. So the current process request input output cannot continue in execution. So the CPU switch to the another ready process. Interrupt occurrence, and we have then external event if we have like hardware or system interruptions temporarily stops the running process and then require to the operating system to the context switch. So here is the main theme matter why the context switch is doing is context switch enable multitasking to multiple process is appearing on the runtime simultaneously and have to the its thing overhead because if create overhead the CPU is not doing useful working with context switch. Efficient context switch improve system performance. So context switch is playing a key role to process management and responsibly to the operating system to execute process effectively and get the performance highly. Thank you. Now, I would like to invite Samkas to explain the next topic. Thank you.
Thank you, Al-amin. I'm Sayham. My ID slash four digit is 1255. Good afternoon and assalamu alaikum everyone to our presentation. And in this part, I will talk about process scheduling. So, process scheduling is just a core mechanism that allows modern computers to run multiple programs concurrently, making efficient use of the most critical resources, the CPU. Our goal is to understand how the operating system decides which task runs, when it runs, and ultimately maximizing CPU utilization. In the figure, we can see the process saves the P1 state, then the process P2, then it again restores the P2, then process happens, the P2 saves the P2, and then the P1 restore. So here we can see the how our operating system decides which task will run and our CPU utilize when our CPU will maximizing the CPU utilization. So in this part, we will start by defining process scheduling queues that holds the process waiting for the different resources. Next, we'll look at the CPU schedulers, the components that makes the decisions. We'll distinguish between the types of scheduling, preemptive and non-preemptive. Finally, we'll do the quick overview of major scheduling algorithms like SCFS, SJFS, and round robin. Next slide, please. So, scheduling queues. Scheduling queues. Before we go on to the slide, it resides one of our several queues like job queue, ready queue, and device queue. So in the figure, we can see the job queue. Job queue is a pool of all processes that have entered the system, often residing in secondary storage. And the ready queue is contains all the processes that are currently in main memory and are ready and waiting for the CPU. That will be on our queue. The CPU scheduler directly pulls it from the CPU. The device queues are specific queues where process waits for a particular I/O device like disk or printer. In the in the right side diagram, we can see the job queue. It will go to the ready queue. Like we already talked about the ready queue, which is contains all the processes that currently in our main memory and are ready to execute the process. Uh, then it will go to the CPU. The CPU will process all the processes, and after the wait is over, it will go to our I/O waiting queue. Then it will go to the I/O, and then it will directly to the ready queue again. Because the device queues are specific queues where process waited for the particular I/O devices, like disk and our printers. So this process starts in the job queue, moves to the ready queue, runs on CPU, and might then be moved to the device queue. If it needs I/O, eventually cycling back to the ready queue until it terminates. Next slide, please. CPU schedulers. We can see the three terms here: long-term CPU scheduling, short-term, and the medium-term. The long-term scheduler or the job scheduler runs infrequently, and it decides process from the job queue are loaded into the memory to the join to the ready queue. So this controls degree of multiprogramming, how many processes are currently competing for the CPU. Short-term scheduler. We can say the CPU scheduler also. It is the most important and run very frequently, like in the milliseconds it runs. It selects the next process to be executed from the ready queue. So which process are waited, it will be go through to our CPU scheduler and it will be executed from the ready queue. The medium scheduler. It actually handles the swapping. It can remove a process from memory to secondary storage. That means the swap out the process from the memory secondary storage and bring it back later, like swap in. This is typically used in manage and reduce the degree of multiprogramming if memory becomes constrained. So I hope we understand the CPU schedulers, the long term, short term, and medium term, how they works. Next slide, please. Types of scheduling. So in the types of scheduling, we have two types, preemptive and non-preemptive. The scheduling decision defines one of two schedulers like preemptive and non-preemptive. Actually, we mostly use the non-preemptive types. Once the progress gets the CPU, it holds on to it until it voluntarily gives gives it up, either by finishing or switching to a waiting state. It is called the non-preemptive. This is simple and inflexible. Preemptive type. This is more common in modern OS. The CPU can forcibly taken away from a running process, usually by a timer interrupt, to give it to a higher priority process or simply to enforce fairness. This requires special hardware support, like a timer, but leads to much better responsiveness. Next slide, please. Scheduling algorithms. With that context, let's now briefly look at the how short-term scheduler actually makes that critical decisions. The scheduling algorithm is the heart of decision-making process. So let's start with the FCFS, the first come first serve algorithm. The most straightforward algorithm is first come first serve, which operates exactly like a waiting line or a FIFO queue. The process that arrives first is executed first. While easy to implement, it has a major drawback called convoy effect. Imagine a very long CPU intense process arriving just before many very short ones. All the short, quick processes have to wait for the single long one to finish, leading to a high average waiting time to the poor utilization of resources. So it has a drawback we can see. Now let's talk about the shortest job first algorithm, SJFS. The SJFS algorithm solves the conveyor effect. So we have the solution of our previous algorithms problem. Conveyor effects are solved in the SJFS algorithm. by prioritizing the process with the smallest expected CPU burst time. The key benefit is the SJFS is proven to be optimal, meaning it guarantees the minimum average waiting time for a given set of processes. However, it practically is limited, but it's impossible to know the exact length of a process next burst ahead of time. It's often approximate or used in a primitive version called SRTF, shortest remaining time first. So we can also use the SRTF algorithm instead of the SJFS algorithm. Now let's talk about our main algorithm, the important one, round robin. Finally, round robin is the algorithm designed specifically for time sharing systems where responsiveness is key. It's primitive and based on FCFS. Here's a small unit of time called time quantum is defined. Each process gets a CPU for at most one time quantum. If process doesn't finish its interrupt and plays at the tail of the circular ready queue to wait for its next turn. It ensures that every process gets fair access to the CPU, guarantees fast response times, which is essential for interactive users. So, in conclusion, we can say process scheduling is the fundamental mechanism that allows an OS to manage concurrent execution effectively by managing queues and using different scheduling algorithms. We ensure the CPU is busy and users get responsive performance. So now we can decide our algorithms like the round robin is the most efficient algorithm. It has the time quantum and using burst time. So it has the less time complexity from our other algorithms. This is for me now, and I would like to my next team member Tawfiq to continue the slides. Thank you.
Assalamu alaikum everyone. My ID last four digit is 1941 and my name is MD Yeasir Arafat Toufick. And today I am going to be talking about the inter-process communication or IPC. In the world of operating system, we often think about programs running in isolation safe and secure in their title bubbles. But in reality, useful software really works along. Today, we'll explore the mechanism of allows that the independent process or to talk each others and synchronize actions and exchange data types by data systems. So at first, we have to know the what is IPC. In definition, a set of mechanism provides by the operating system allows process to manage shared data. So there are three components that cooperation, synchronization, and data exchange. Cooperation allowing that independent process to work through towards a single goals, and synchronization ensure that the process does not trip is over others, that like a process is writing a message in the same location at the same instance, b processes overwrite it. And the data exchange is simply moving information from process A to process B. So why we need IPC? So IPC need is various cases uh, that uh, everyone can ask that why we go through this travel and why not just running on massive program. There are four main reasons we need IPC. Information sharing. So in this section, open multiple users or application need access to the same data like a central database being accessed by website and internal analysis tool simultaneously. Competition speed up. Uh, if we have a heavy task, we can break it into subtasks and run them in parallel on different CPU process. IPC allows these subtasks to combine their results and make this happen. Modularity. It allows us to build system like Lego blocks. If we build a system with separate communicating process like multiverses, it much easier to maintain the debug and the on giant block of code. And then convenience. For us as user, uh, it allows multitasking. We can copy data from a spreadsheet and pass it into document. The transform requires the two programs to communicate. In this section, these are performing the execute the program in a little part and make a big giant program. Primary IPC methods. So primary IPC methods. Now, how to do actually implement this? There are two primary architecture models. First, on the left, and we have shared memory. So imagine a whiteboard is a conference room. Multiple people can work up and write on it. It's extremely fast because the OS does not have a intervals. The first sorry, the interface for the every single row to read or write. However, it requires careful synchronization. If two people write over each other, you get garbage data. Then secondly, we have message passing. This is more like sending emails, process exchange messages via the OS kernel. This category includes things like pipes, connecting the output of the command and to another, and escape just the messaging communicating over a network. It is generally slower than shared memory because the OS has managed the message, but it much easier to implement safely. And then comparing models. So in the here is the visual comparison two models in the right side of my slide. The shared memory scenes of the left and establish uh, establish a region of memory that both process A and process B can access directly if this efficiency for large amount of data. But as I mentioned, the complexity lies in the synchronization avoided restriction. Message passing in the right users the kernel on the active model process A sends the message and kernel, and the kernel handles the process B. This is the standard distributed system because it does not rely on shared variables, making the ideas and communication different with the different computers. So now we'll see the real world example of the IPCs. We can use IPC every day, but we do not notice this. So I will tell you how we use the IPC regularly. Just think about the Chrome browser, the most common and knowledgeable this browsers. Uh, uh, you will notice that even that if the tab is Chrome crashes, the whole browser does not close. That because Chrome's every tabs as a separate process. They use IPC to talk or to maintain browser engine. Is this isolation or improves stability? The clipboard, the simple acts of the copy and paste. It is closely IPC example. The operating system holds a data buffer and on application writes and another reads from. The client server architecture. Finally, we entered the inbuilt on IPC. How we browser request a web page, it is usually shocks to perform IPC with a web server that might be on the other side of the world. Uh, at last, we are go ahead to the conclusion of this presentation. So in conclusion, that the IPC model communicate with backends of the model over thing, and that we uh, we talk about the process communication and another the operating system OS. This is the very closely related to each others, and this function makes the future or more better, and this maintain the stability, and the it helps to solve the big problem into part of a small problem, and it very essential for every developers and users to execute that. And shared memory for a game engine and message passing and server is I would say make the system soothing and functionals. uh, Thank you everyone. That's for all. Thanks for listening.